Imagine a basement laboratory, buried deep underground, safely away from the chaotic tremor of the surface world. The air is thick with a low, rhythmic hum. It is the sound of heavy machinery working relentlessly to erase heat, vibration, and the random noise of the physical universe itself. The entire purpose of this engineered isolation is focused on a sealed metallic chamber. Inside, suspended within an invisible cage of intersecting electric and magnetic forces, is a single electron. It is completely alone. The space around it has been cooled so close to absolute zero that the natural thermal motion of the universe essentially stops. In that profound stillness, scientists did not try to look at the electron. Instead, they measured the way it responded to the magnetic field holding it. They were measuring its magnetism. They measured it with an exactness that borders on the surreal, pulling their answer out of the quiet dark. The number was 1.00115965218.059. That string of numbers represents a deep agreement between the human mind and the physical world. Long before this electron was trapped, theoretical equations had predicted what that measurement would be. When the results were tallied, theory and measurement agreed to about 1 part in a million. This is the most precisely tested prediction in the history of science. But if you follow its mathematics to their absolute edges, you find something deeply unsettling. By the strict standards of pure mathematics, the theory behind that incredible number has never been shown to actually exist. We are the unknown. Tonight, we are descending into the deepest and most successful framework in modern physics to explore the strange gap between ultimate precision and absolute certainty. We will see how a theory can be undeniably right without ever being proven to be real. When you leave the surface of the world and descend deep underground, you begin to leave behind the scale of human life. Up above, there is the chaotic, unpredictable noise of weather. There is the constant shifting tremor of traffic, the vibration of footsteps, the endless hum of radio waves and cellular networks passing through the air. The surface of the Earth is a place of constant agitation. But as you travel down into the basement of a physics laboratory, you enter a space that has been engineered to forget all of that. Down here, there is only the thick, steady hum of the apparatus. It is a deep mechanical drone. It is the sound of heavy compressors and vacuum pumps working continuously, relentlessly, to isolate one tiny, fragile volume of space from the rest of the universe. Inside the machinery, at the very heart of the experiment, lies the trap. And inside the trap lies the profound silence of a cooled vacuum. To cool something down is simply to slow it down. Heat is nothing more than motion. The warmth of a summer afternoon is just the air moving quickly against your skin. The biting cold of a winter night is simply that motion slowing down. In this laboratory, they have slowed the motion down to a near absolute stop. They have cooled the trap to a fraction of a degree above absolute zero. At that temperature, almost all thermal vibration ceases. The atoms in the metal walls of the chamber freeze into a stiff, silent grid. The empty space within the chamber becomes as still as anything in the physical universe can possibly be. It is an environment of profound, almost impossible stillness. And in that ultimate stillness, held softly in place by an invisible cradle of electric and magnetic fields, sits one single electron. What is it doing there? To understand the weight of this experiment, you have to understand what it means to isolate an electron. We are used to thinking of matter in chunks. A grain of sand, a speck of dust, a single cell. But all of those things are sprawling, chaotic cities of matter compared to this. An electron is a fundamental building block of reality. As far as modern physics can tell, it is not made of anything else. It cannot be broken open. It has no internal gears, no hidden mechanisms. It has no physical size at all. It is a point. It is a pure, irreducible feature of the universe. Normally, electrons are busy. They are swarming around the nuclei of atoms, binding molecules together, flowing through wires to power the lights in your room. They are never alone. But in this trap, this one single electron has been stripped away from all of that. It has been separated from every atom, hidden from every stray molecule of gas, shielded from every flash of radiation. It is completely, utterly alone. It is held in the dark, suspended in a magnetic cage, waiting in the silence. And it is waiting because the scientists who put it there have a question. They have gone to these extraordinary lengths, building a machine that hums endlessly just to hold this one invisible speck in the dark, because when you isolate a fundamental piece of the universe and remove all the noise, you can ask it a question. And if you listen with enough patience, it will give you an answer. The question they wanted to ask was about magnetism. They wanted to know the exact magnetic strength of the electron. To understand what they were measuring, you do not need to know the mathematics, and you do not need to know the equations. You only need to imagine the way charged things behave when they move. The universe has a rule. If you take an electrical charge and you move it in a circle, it creates a magnetic field. It acts like a tiny bar magnet with a north pole and a south pole. This is the basic principle behind the electromagnets in everyday motors. The property that describes how strong that tiny magnet is and exactly how it will react when placed near other magnetic fields is called its magnetic moment. For a long time, early physicists pictured the electron in exactly this way. They imagined it as a tiny electrically charged sphere spinning endlessly on its axis, like a miniature planet. If it was a spinning sphere of charge, it would naturally generate a magnetic moment. But the deeper physicists looked, the stranger reality became. We just established that an electron is not a tiny solid ball. It is a point. It has no physical volume. It has no surface to spin. And yet, despite having no physical size, it carries an electrical charge. And despite not being a solid object that can physically rotate in space, it possesses a fundamental intrinsic quantum property that physicists call spin. It is as if the universe simply assigns the property of spinning to the electron, permanently and irreversibly, without giving it any physical substance to actually spin. Because it has a charge, and because it has this intrinsic quantum spin, the electron has a magnetic moment. It acts as a magnet. It interacts with magnetic fields. It is a permanent, tiny magnet built into the fabric of the world. So how do you measure the strength of a magnet that has no size, sitting in pitch darkness, cool to absolute zero? You cannot look at it. There is nothing to see. Instead, you listen to how it responds. When the electron is placed inside the trap, the magnetic field of the trap pushes against the magnetic field of the electron. The electron responds to this push. It wobbles, it precesses. It moves much like a spinning top wobbles as it slows down on a wooden floor, its axis tracing a slow circle in the air. By carefully, patiently listening to the exact frequency of that wobble, physicists can calculate the electron's magnetic moment. This is not a measurement you can make in a single afternoon. It requires holding the electron perfectly still, keeping the environment perfectly cold, and letting the hum of the cooling apparatus run for long periods of time while data is slowly and meticulously collected. The signal is incredibly faint. It is a whisper from the microscopic world. It takes profound dedication. and an almost unnatural level of stillness to hear it clearly over the background noise of reality. You are listening to the fundamental wobble of a single point of charge. The physicists who dedicated themselves to listening to that whisper were X. Fan, T. G. Myers, B. A. D. Sucre, and G. Gabriels. They worked at Harvard and at Northwestern University's Center for Fundamental Physics. What they did was not simply run an experiment. It was the culmination of decades of refined technique. It was the result of a long, slow process of learning how to build better traps, how to achieve deeper vacuums, how to hold the temperature steadier, and how to isolate the room more completely from the trembling of the world above. In February of 2023, they published their final result in the journal Physical Review Letters. They had successfully measured the magnetic moment of the electron, and they had done it with an uncertainty of 0.13 parts per trillion. Before this result was published, there was an older measurement of the electron's magnetic moment. That older number was a masterpiece of experimental physics in its own right. It stood as the undisputed best measurement in the world for 14 long years. Every theorist and every experimentalist relied on it. But the new measurement by Fan, Myers, Sucre, and Gabriels shattered that record. It was 2.2 times better than the value that had stood for 14 years. To give you a sense of how difficult this achievement is, the physics community also studies a heavier cousin of the electron called the muon. The muon has its own magnetic moment, and measuring it takes a storage ring the size of a building and an international collaboration working for years. Yet the measurement of the single electron, sitting alone in this quiet basement trap, is 3,000 times more precise than the equivalent measurement of the muon. This result tests the standard model of particle physics to 1 part in a million. The standard model is not just a single equation. It is the crowning achievement of 20th century physics. It is a vast, intricately connected mathematical architecture that attempts to explain exactly what the universe is made of and exactly how those pieces interact. It describes the light from the sun, the forces holding your body together, and the invisible fields that govern the stars. Theorists have spent entire lifetimes pushing this model to its limits, trying to calculate what it predicts for the simplest properties of the simplest particles. It is this model, this sprawling monument of human thought, that was put to the test in that quiet basement. We need to pause here. We need to stop and truly understand what that level of precision actually means. Human beings are not evolved to comprehend numbers like 1 part in a million. When a number gets that incredibly small or that vastly large, it becomes an abstraction, it becomes a blur in the mind. It loses its physical reality. So we have to map it onto a scale that we can feel. We have to anchor it in the physical world we know. Imagine the distance from the Earth to the Moon. It is a vast, cold gulf of empty space, stretching out for roughly 239,000 miles. Imagine that you are given the task of measuring that exact distance. You lay down your ruler, you stretch out your tape measure, and you calculate the entire journey across the dark void, all the way from the surface of our world to the dusty craters of the lunar surface. If your measurement of the distance from the Earth to the Moon was accurate to 1 part in a million, you would not be wrong by a mile. You would not be wrong by a foot. Your measurement of the entire distance to the Moon would be wrong by about the thickness of 4 sheets of paper. Imagine crossing 239,000 miles, arriving at the Moon, and finding that your predicted destination is off by nothing more than the thickness of 4 sheets of paper. That is the level of precision we are talking about. That is what 1 part in a million actually means in the physical world. And that is the exact level of precision to which the theoretical prediction and the laboratory measurement of the electron's magnetic moment agree. Because long before this specific electron was ever trapped, long before the cooling machinery was ever turned on, the theorists had already done their work. Using the framework of the Standard Model, they had calculated what the magnetic moment should be. The mathematics involved in that calculation are staggeringly complex, taking years of careful arithmetic to resolve. But they produced a number. When the experiment was finally finished, when the hum of the apparatus settled and the data was analysed, the measured number and the theoretical number were compared, and they agreed to about 1 part in a million. When a theoretical framework predicts a number, and an experiment measures that number, and they agree to the equivalent of 4 sheets of paper across the distance to the moon, we are forced to admit something profound. This is not a lucky guess. This is not a coincidence. You do not accidentally predict reality to that depth. When the equations were written down, they did not just describe a neat mathematical idea. They described the actual, physical universe. They anticipated exactly how a single invisible particle would wobble in a magnetic trap inside a cold basement decades later. They got it so unbelievably right that it seems impossible to deny that the theory is a true reflection of nature. It is the most precisely tested prediction in the history of science. But precision is not the same thing as certainty. The map can be flawlessly accurate, and yet fundamentally incomplete. And the rest of the night lives in the gap between them. In the year 1687, the human understanding of the physical universe changed in a way that is difficult to overstate. Before that year, humanity lived in a divided world. There was the earthly realm, where things were heavy, where apples fell from trees, where carts had to be pushed through the mud, and where everything eventually ground to a halt. And then there was the heavenly realm, the stars, the planets, the wandering lights in the night sky. For thousands of years, it was assumed that the heavens were made of a completely different substance. They were perfect, they were eternal, and they moved according to divine rules that had absolutely nothing to do with the dirt and the gravity of Earth. It was in the year 1687 that Isaac Newton published a book that would come to be known simply as the Principia. Within its pages, Newton took a hammer to that ancient division. He presented a mathematical framework that unified the earthly and the heavenly into one single, unbroken system. Newton showed that the exact same invisible force pulling an apple from a branch down to the grass was the exact same force curving the moon in its long, silent orbit around the Earth. He gave us universal gravitation. The word universal is the most important part of that phrase. It meant one rule for everything, everywhere. It was a staggering triumph of human reason. It allowed astronomers to look up at the sky and predict the paths of comets and the timing of eclipses with astonishing accuracy. For the first time in human history, the universe seemed truly comprehensible. It was the birth of modern theoretical physics, and it painted a picture of the universe as a giant, predictable clockwork machine, ticking away in the dark, entirely obedient to mathematics. But beneath the brilliant triumph of that mathematics, there was a quiet, lingering discomfort. And no one felt that discomfort more acutely than Newton himself. The problem was not with the math. The equations worked perfectly. The problem was with the physical mechanism behind the math. If the Earth was pulling on the moon, how exactly was it doing it? The Earth and the Moon are separated by hundreds of thousands of kilometers of empty space. There is no rope tying them together. There is no chain, no invisible scaffolding, no physical connection of any kind bridging that dark void. How can a physical object reach across a vast gulf of absolute nothingness and exert a physical force on something else? Think about how deeply counterintuitive that is. If you want to move a stone, you have to push it with your hand or hit it with a stick. You must make contact. But gravity makes no contact. This deeply troubling idea was known as action at a distance. It was the suggestion that matter could affect other matter across a gap without anything in between to carry the signal. It felt like magic, and Newton despised magic. He found the idea philosophically deeply unsatisfying. He knew his equations could describe exactly how gravity behaved, but he famously refused to guess what gravity actually was. He would not invent a hypothesis to claim he knew the hidden machinery of the universe. He provided the rules, but he admitted that the empty space between the planets remained a profound mystery. For more than a century, physics accepted this strange, uneasy compromise. Gravity worked, even if no one could say how the pulling was done. It took a completely different kind of mind to solve the problem of the empty gap. In the early 19th century, Michael Faraday was working in a laboratory in London. Unlike the wealthy, university-educated aristocrats of his era, Faraday came from a poor background and had almost no formal mathematical training. He could not write down elegant, towering equations. He understood the world differently. He understood it through intuition, through physical observation, and through a brilliant, unparalleled ability to run experiments with his own two hands. He could see how things behaved in the physical world and imagine the unseen forces pulling the strings. It was a different kind of genius, one rooted entirely in the physical reality of the laboratory. One of his most famous experiments is something you may have seen done in a classroom. It is beautifully simple. Faraday placed a common magnet underneath a flat, white sheet of paper. He then took a handful of iron filings and sprinkled them gently over the surface of the paper. If you close your eyes and listen closely in the quiet of a laboratory, you can almost hear the faint rasp of iron filings settling onto paper. It is a dry, whispering sound, like sand falling on dry leaves. When those tiny pieces of metal landed, they did not just scatter into a random, chaotic pile. Guided by an invisible hand, they arranged themselves into beautiful, sweeping curves. They formed distinct, organized paths that looped out from one end of the magnet, arched across the empty space of the paper, and returned to the other end. You could tap the paper gently, and the filings would jump and settle even more perfectly into these curving lines. To Faraday, watching the iron filings trace these invisible paths, the empty space around the magnet did not look empty at all. It looked structured. How did the iron know where to go? How did a tiny filing sitting an inch away from the magnet know it was supposed to align itself perfectly with its neighbours? Action at a distance said that the magnet was magically reaching across the empty space and grabbing the iron. But Faraday proposed a radically different idea. He proposed that space itself carries a condition. He called them lines of force. He suggested that the magnet was not reaching out to the iron at all. Instead, the magnet was altering the very fabric of the space around it. This was the birth of the field. It is arguably the most important conceptual shift in the history of human thought. We have to be very careful to understand exactly what shifted here, because it is the foundation of everything that comes after it. In the old way of thinking, an object reaches across an empty gap and pulls directly on a second object. The space between them is dead and empty. In Faraday's new way of thinking, an object creates a field around itself. That field permeates the space, like tension in a spiderweb. When a second object enters that space, it does not interact with the distant magnet. It interacts with the field right where it is standing. The action is no longer distant. The action is local. The field is the mediator. The field is the invisible condition of space that tells the iron filing how to move. The gap between objects was no longer empty. The universe was suddenly filled with invisible tension, invisible structures, invisible lines of force waiting to be felt. But Faraday could not speak the language of higher mathematics. His lines of force were viewed by many of his contemporaries as a useful mental picture, a helpful way to visualize magnetism, but not a rigorous scientific theory. It was not until the 1860s that a Scottish physicist named James Clerk Maxwell translated Faraday's brilliant intuition into the strict, unforgiving language of mathematics. Maxwell took the curving lines of force and gave them formal equations. He studied the electric field and the magnetic field, and he discovered that they were not separate phenomena. They were deeply, intimately intertwined. Maxwell's equations revealed a beautiful, hidden machinery operating in the background of the universe. They were elegant, symmetric, and profound. He showed that a changing electric field creates a magnetic field, and a changing magnetic field, in turn, creates an electric field. One gives rise to the other in a perpetual, alternating dance. If you disturb an electric field, it creates a magnetic ripple, which creates an electric ripple, which creates a magnetic ripple. Together, they push each other forward. They pull each other into existence, traveling through space as a single, self-sustaining wave. When Maxwell calculated the speed at which this combined electromagnetic wave would travel, the mathematics gave him a number. It sat right on top of the measured speed of light. In that moment of pure mathematical revelation, the nature of light was finally uncovered. The soft glow of a candle, the radiant heat of a fire, the blinding glare of the sun, none of them were tiny bullets of matter shooting through an empty void. They were ripples. They were vibrating waves travelling through the electromagnetic field. The universe was not an empty vacuum containing a few scattered rocks. It was a structure of fields, everywhere at once, quietly holding a value at every point in space. This is the world as modern physics understands it, a world where empty space is never truly empty, and where the forces that bind us are carried by an invisible, humming web that fills every corner of the universe. It is a staggering picture of reality, built slowly by men staring at iron filings and wrestling with equations. Before we move deeper into the strange world that these fields eventually unlocked, I want to take a brief, quiet moment to ask something of you. If you have found something worth staying for tonight, please consider following the show on whatever platform you are listening on right now. It is the single best way to ensure that our future episodes find their way to you, and we would be honoured to have you with us. Because the story of the field does not end with Maxwell in the 19th century. It was only the beginning. The realization that light was a ripple in a field changed everything about how we understand reality. It meant that when you stand outside on a clear night and turn your face toward the stars, the light reaching your eye has not been crossing nothingness for millions of years. It has been a disturbance in the electromagnetic field itself, not a wave in some invisible jelly-filling space, which is a picture physics tried for a while and then abandoned. The field is not a substance that waves. The field is the thing that has a value at every point, and the wave is that value changing. Before the star ever ignited, before its light ever began its long, lonely journey toward the Earth, the capacity for that light to travel was already waiting in the dark. The field was already there. By the end of the 19th century, physics had built a magnificent, continuous world. It was a world of smooth curves, flowing energy, and fields that stretched seamlessly across the empty vacuum. It felt complete. It felt like the final word. But right at the dawn of the 20th century, in the year 1900, that smooth world was abruptly broken apart. It was broken by a man who had absolutely no intention of breaking it. His name was Max Planck, and he was trying to solve a very specific, stubborn problem about how hot objects radiate heat and light. It was an incredibly mundane problem on the surface. If you take a piece of iron and place it in a hot forge, it begins to glow. First it glows a dull red, then a bright yellow, and if you get it hot enough, it glows a blinding white. You can feel the heat radiating off it from across the room. According to the smooth, continuous physics of the time, an oven heating up like this should eventually radiate an impossible, infinite amount of high-frequency energy. The math said that every time you opened a hot oven, you should be blasted with a lethal dose of invisible radiation. This was obviously, glaringly wrong. The real world did not work that way. To fix the equations, to make the math match the quiet reality of a glowing piece of iron, Planck introduced a mathematical trick. He suggested that energy could not be emitted in a smooth, continuous flow. Instead, it had to be emitted in tiny, indivisible, discrete chunks. He called them packets, or quanta. It was a desperate, reluctant move. The emotional center of this discovery is not a scientist shouting in triumph. It is a man deeply troubled by his own work. Planck was a conservative thinker. He loved the continuous, elegant physics of the past. He did not trust his own answer. He viewed these packets of energy as a mathematical bookkeeping device, a temporary fix to make the equations balance. For years after he published his work, Planck did not accept that these packets were physically real. He spent a great deal of his own life trying to find a way to undo what he had done, trying to return the universe to a smooth, continuous state. But the mathematics refused to budge. The packets were there. Then, in the year 1905, Albert Einstein took Planck's reluctant mathematical trick and made it painfully, physically real. Einstein was looking at something called the photoelectric effect. This was a phenomenon where, when you shine light on a piece of metal, the light can actually knock electrons loose from the surface. It acts like a tiny, invisible hammer hitting a bell, knocking pieces of the metal's electrical charge away. But the way it happened made absolutely no sense under the old, continuous rules of the universe. If light was just a continuous flowing wave, like water washing over a beach, then making the light brighter should give it more power to knock electrons free. A bigger wave should do more damage. But that is not what happens in the laboratory. If you shine a blazing, blindingly bright red light on the metal, nothing happens. Not a single electron moves. You can bathe the metal in red light until it heats up, and still, the electrons remain perfectly trapped. But if you turn off that blinding red light, and you shine a very dim, faint blue light on the same metal, electrons immediately fly off. Einstein realized that Planck's reluctant packets were the only way to explain this strange behavior. Light was not a continuous flow. It was a rain of individual packets, and the mechanism is beautifully concrete. Making a light brighter does not make the individual packets stronger. Brighter light simply means there are more packets falling. It is the color of the light, its frequency, that sets the amount of energy carried by each individual packet. A single packet of red light simply does not have enough energy to knock an electron loose. You can shine a blinding red light on the metal all day, raining down billions upon billions of weak packets, and nothing will happen. But a single packet of blue light, because of its higher frequency, carries a heavier punch. Even if the blue light is incredibly dim, meaning there are very few packets, the ones that do hit the metal have enough energy to knock an electron free. Dim blue light can do what blazing red light cannot, because light is not a smooth wave of energy. It arrives in distinct, separate, physical pieces, carrying discrete amounts of energy that cannot be broken down any further into smaller fractions. The strangeness only deepened. In the year 1913, Niels Bohr took this idea of the quantum packet and applied it to the inside of the atom itself. He proposed that the electrons swarming around an atomic nucleus could not just orbit anywhere they pleased. They were restricted to very specific, allowed energy levels. They could be in one orbit, or they could be in the next orbit out, but they could not exist anywhere in the space between. We must be honest here. Bohr's picture of the atom, with electrons circling the centre like little planets circling a sun, is a stepping stone. It is not the final true picture of reality. It was a necessary bridge, a way for the human mind to begin grasping the bizarre rules of the microscopic world. But even as a stepping stone, it changed everything. It explained why atoms were stable, and why they only emitted very specific colours of light. Then, in the year 1924, Louis de Broglie pushed the door open all the way. He made a profound leap of logic. If light, which everyone had always believed was a wave, could sometimes act like a particle, then matter, which everyone had always believed was made of solid particles, must also have an associated wavelength. If you find yourself drifting off somewhere in here, lulled by the quiet recitation of names and dates, that is perfectly all right. You do not need to memorize the timeline to feel the weight of what these people found. You can simply let the rhythm of the history wash over you. The details will wait for you. None of this is going anywhere in the dark. The essential truth is that the rigid, absolute wall between a wave and a particle was collapsing. A piece of physical matter was no longer just a hard, tiny dot. It had a wavelength. It had a frequency. It spread out. So what does all of this microscopic strangeness actually mean for you, living your life at the human scale? It means everything. Think about your own hand. Imagine resting it right now on a wooden table, or against a fabric chair, or simply touching your own arm. Press down. You feel resistance. You feel solidity. Why does it feel solid? Why doesn't your hand pass right through the wood as if it were air? We are taught from a very young age that objects are solid things. We are told that matter takes up space. But physics tells us that atoms are overwhelmingly, almost entirely made of empty space. If you were to blow up an atom so that its nucleus was the size of a marble sitting in the centre of a football stadium, the electrons would be tiny specks swarming way up in the highest seats. Everything in between is nothingness. If your hand is made of empty space, and the table is made of empty space, why do they crash into each other so firmly? Why doesn't the empty space of your hand just slide harmlessly through the empty space of the wood? It is not because the atoms are packed together like physical bricks. It is because of the electromagnetic interaction between the negative electrons in your hand and the negative electrons in the table. Like magnets repelling one another, they push against each other. But there is a deeper, much more absolute rule at work underneath that repulsion. It is called the Pauli exclusion principle. This is a strict, unbreakable quantum rule that completely forbids certain types of particles, like electrons, from occupying the exact same quantum state at the exact same time. The electrons in the surface of your hand literally cannot share the same physical state, the same space and energy, as the electrons in the surface of the wood. The rules of the universe simply will not allow it, and so they push back, they resist. The resistance you feel when you push against a heavy oak table is the resistance of quantum exclusion. This means that solidity is not a starting ingredient of the universe. The universe does not begin with hard, solid things. Solidity is a consequence. It is an outcome of fields pushing against one another, and of strict underlying quantum rules dictating where particles are allowed to be. By the 1920s, physics found itself staring at a profound contradiction. On one side, they had Faraday and Maxwell's beautiful fields. A field is a value at every point in space. It undulates, it changes, it flows continuously. On the other side, they had Planck and Einstein's packets, discrete, indivisible, undeniable chunks of reality that refuse to be smoothed out. The universe was continuous, and the universe was broken into pieces. Both things were proven. Both things were true. Physics now had fields, and it had packets, and nobody could yet say exactly how a packet lives inside a field. No one knew how a discrete, solid-seeming thing could emerge from a continuously changing value spread across empty space. It would take a new generation of minds and a new kind of mathematics to finally weave the two ideas together. But whatever that final answer was going to be, the groundwork was already laid. Before the first packet of light was ever recognized, before the rules of quantum exclusion were ever written down, the foundation was waiting in the dark. The field was already there. By the late 1920s, physics was caught in a deep and profound tension. As we saw, the universe was suddenly divided. On one hand, you had the continuous, flowing fields of electromagnetism. On the other, you had the sharp, undeniable reality of quantum packets, the discrete chunks of energy and matter. But there was another tension, one that was even more immediate and mathematically pressing. The new rules of quantum mechanics were incredibly successful. They could describe an electron sitting quietly in an atom. But quantum mechanics had a massive blind spot. It completely ignored Albert Einstein's theory of special relativity. Special relativity governs how things behave when they move incredibly fast at speeds approaching the speed of light. If you had a fast-moving electron, quantum mechanics and special relativity fundamentally disagreed on how to describe it. They were two of the most successful frameworks ever devised by the human mind, and they were speaking entirely different languages. In the year 1928, a brilliant, notoriously quiet physicist named Paul Dirac set out to fix this. Dirac was a man who believed absolutely in the power of mathematical beauty. For him, mathematics was not just a tool to describe the physical world, it was a fundamental truth. He believed that if an equation was beautiful, elegant, and logically sound, it had to be true even if the physical world had not yet revealed that truth to human eyes. He wanted to find a single, unified mathematical description of the electron. He wanted one equation that satisfied the bizarre, probabilistic rules of quantum mechanics, while perfectly obeying the strict speed limits and energy laws of special relativity. It was a staggering mathematical puzzle. It required balancing highly complex matrices, working with abstract numbers, and finding a structure that simply did not exist in the physics textbooks of the time. But Dirac found it. By trusting the mathematics, he wrote down what is now known simply as the Dirac equation. It successfully married quantum mechanics and special relativity for a single electron. It was a masterpiece of theoretical physics, an elegant structure built entirely out of logic. But almost immediately, the equation began to behave in a way that Dirac had not anticipated. When you solve a simple algebraic equation, like finding the square root of a number, you often get two answers. The square root of 9 is 3, but it is also -3 because -3 multiplied by -3 is still 9. When Dirac solved his massive complex equation for the electron, a very similar thing happened. The mathematics returned extra answers. It returned the normal, expected description of the negatively charged electron. But the math stubbornly produced a second set of solutions. This second set described a particle that was exactly identical to the electron in every single way, with the exact same mass, the exact same spin, but with one glaring difference. It had a positive electrical charge. It was a perfect mirror image. Dirac was hesitant. He was deeply cautious about claiming that this was a brand new particle. He tried for a short time to explain it away, suggesting perhaps the extra math was just a description of the proton, a heavy positive particle that was already known, but the math simply would not allow that. The proton was far too heavy. The equation was unyielding. It demanded a particle that no human being had ever seen, a particle that no one had ever asked for, and a particle that no one even suspected might exist. Dirac did not set out to add antimatter to his theory. He did not build it in on purpose. His theory simply handed it to him. For 4 years, the mathematics sat on the blackboard, an elegant prediction hanging in the dark, waiting for reality to catch up. Then, in the year 1932, an experimental physicist named Carl Anderson was studying cosmic rays. These are high-energy particles raining down on the Earth from deep space. He was using a device called a cloud chamber, which was essentially a sealed box filled with a supersaturated vapor. When a charged particle passes through this vapor, it leaves a tiny, visible trail of condensation, much like the white contrail left behind by an airplane high in the sky. By placing this chamber inside a strong magnetic field, Anderson could see not only that a particle had passed through, but he could watch how the magnetic field bent its path. Because of their electrical charge, negative particles would curve one way in the magnetic field, and positive particles would curve the other way. But, as he looked closely at the photographs produced by his chamber, Anderson found a track that simply did not make sense according to the known rules of physics. It was thin and light, exactly like the delicate track of a normal electron. It was definitely not a heavy proton, but it was curving the wrong way. It was a lightweight, positively charged particle. It was the positron, the very first piece of antimatter ever discovered by humanity. Stay with this for a moment, because it is one of the strangest things that has ever happened in science. The confirmation arrived 4 years after the mathematics had demanded it. The equation knew something its author did not. Paul Dirac had followed the strict, logical rules of mathematical beauty, and the math had raced out ahead of human observation, peering into a corner of reality that we did not even know was there. The math knew about antimatter before the universe ever bothered to show it to us. But the discovery of antimatter created a massive philosophical crisis for physics. If you have an electron and you introduce it to a positron, their opposite charges pull them together. When they meet, they completely annihilate each other. The physical matter disappears, vanishing entirely into a flash of pure energy. 2 solid particles of matter simply cease to exist, leaving only radiation behind. And the process works perfectly in reverse. If you have enough pure energy, concentrated tightly enough in one place, you can spontaneously create a brand new electron and a brand new positron out of that energy. Energy condenses back into matter. It is a perfect, flawless exchange. A heavy particle and its antimatter twin can disappear into a bright flash of light, and that exact same flash of light, if it is concentrated enough, can tear itself apart to become physical matter once again. The boundary between matter and energy completely dissolves. This meant that particles were not permanent. If you build a massive machine and you collide two particles together hard enough, the sheer energy of that collision can create entirely new particles. You can literally get out more physical objects than you put in. How do you write a theory of the universe when the pieces keep changing? For centuries, the fundamental assumption of science was that the universe was built on a fixed inventory of little objects. You might move the objects around, you might combine them in different ways, but the number of objects fundamentally stayed the same. But a theory built on a fixed inventory of little objects absolutely cannot describe a world where the number of objects is constantly changing, where matter vanishes into light and light condenses into matter. This is why the modern picture of quantum fields was completely forced upon physics. It was not a stylistic choice. It was not a preference. It was an absolute necessity. You cannot use a theory of fixed particles, but a theory of fields can handle this perfectly. Why? Because a field is continuous. A field can carry one ripple, or it can carry 5 ripples, or it can carry 50 ripples, or none at all. When a particle is destroyed, the ripple simply flattens out, returning its energy to the field. When a new particle is created, the field simply ripples again, absorbing energy and standing up as a new particle. If particles can simply come and go, popping into existence from pure energy and vanishing just as quickly, then the particles themselves cannot be the fundamental building blocks of reality. The fields are fundamental. An electron is not a permanent, solid little ball. An electron is nothing more than a localized excitation, a ripple of energy, moving through the electron field. A photon of light is simply an excitation of the electromagnetic field. Quarks, the particles that make up the protons in your body, are just excitations of the quark fields. Every particle in the universe is just a temporary vibration in an underlying invisible structure. But as we build this picture, we must lay down a strict, unbreakable rule. It is very easy, when talking about invisible, universe-spanning fields, to let the imagination drift into a kind of comfortable mysticism. You must not do that. A quantum field is not a mist. It is not a fog. It is not a glowing spiritual ocean waiting quietly behind the wallpaper of everyday reality. It is a rigorously defined mathematical and physical entity. It possesses a specific, measurable value at every single point in space. It is governed by strict, unforgiving equations. It perfectly obeys the strange, probabilistic rules of quantum mechanics. When we say an electron is a ripple in the field, we mean the electron field is carrying exactly one quantum of excitation there. One, and not a fraction of one, because the rules do not permit a fraction. It is structure, not magic. It is math, not metaphor. The Dirac equation opened the door to this entire view of the world. It showed us that empty space was capable of producing matter and antimatter perfectly paired, born from the energy of the fields. It proved that the universe was far more deeply interwoven and complex than a simple collection of solid, unchanging dots. But, as physics stepped fully into this new reality, it found something waiting for it in the dark. The same beautiful mathematics that had flawlessly predicted antimatter were about to break down in a spectacular way. The same elegant equation that had handed physics the positron The exact same piece of mathematics that had performed this miraculous trick of predicting reality years in advance also handed it its very first paralyzing infinity. The field was already there. It is one thing for a mathematical equation to be complicated. It is a completely different thing for a mathematical equation to be broken. And as the 1930s bled into the 1940s, the beautiful, emerging mathematics of the quantum field seemed to be fundamentally, fatally broken. The problem was agonizingly simple to state. An electron has a negative electrical charge. Because it has a charge, it creates an electromagnetic field around itself. But the electron does not just create the field and leave it behind. The electron exists perfectly inside its own field. So the most obvious, elementary question a physicist can ask is, what does the electron's own field do to the electron itself? How does the particle interact with the space it is disturbing? This is known as calculating the self-energy of the electron. It sounds like a standard homework problem, but when the brilliant minds of the era sat down to calculate this using the strict new rules of quantum mechanics and special relativity, the answer they got was infinity. We need to be absolutely, plainly clear about what that means. Infinity is not just a very large number. It is not a trillion or a quadrillion. It is not a rounding error. It is not a slight miscalculation that can be adjusted away by checking the decimal places or tweaking a dial on a machine. It is a mathematical divergence. It means the equations completely blew up. Think about the physical implications. If the mathematics were literally true, it meant that an electron's own field would push back on it so violently, so absolutely, that the electron should be infinitely heavy. It should require an infinite amount of energy to move an electron even a fraction of a single inch. It should be frozen in place, locked down by the infinite weight of its own electrical disturbance. But we know for an absolute fact that an electron is not infinitely heavy. It is incredibly light. It moves very easily. It dances through wires to light the bulbs in our homes. So the physical reality of the laboratory and the mathematical reality of the chalkboard were staring at each other across an unbridgeable silent gulf. The mathematics were simply broken, and the infinity would not go away. Then came the 1947 Shelter Island Conference. The Second World War had recently ended. During the war, many of the brightest minds in physics had been drafted into the war effort, working on radar at the radiation laboratory or on atomic weapons in the desert. Now, they were finally returning to the pure, fundamental problems of the universe. A small gathering of these physicists met at a quiet inn on an island in New York to discuss the crisis of the infinite electron. At this conference, two men named Willis Lamb and Robert Rutherford presented the astonishing results of an experiment they had been quietly running. They were studying hydrogen gas. Hydrogen is the simplest atom in the universe. One proton in the center, and one single electron orbiting around it. It is the perfect test subject. If your mathematical rules fail to describe hydrogen, they will fail to describe everything else. According to the elegant, beautiful Dirac equation, the exact same equation that had successfully predicted the existence of antimatter years before, two very specific, distinct energy levels inside the hydrogen atom should be perfectly, exactly identical. They should sit at the exact same level, indistinguishable from one another. But Lamb and Rutherford had used advanced microwave techniques, technology born directly out of wartime radar research, to probe the hydrogen atom with unprecedented precision. They had built an apparatus sensitive enough to prove the great Paul Dirac wrong. The two energy levels were not identical. They were separated. The measured separation was 1057.862 megahertz. It was a tiny, microscopic gap, but it was absolutely real. This separation became known as the Lamb shift. It proved, beyond any shadow of a doubt, that the electron was interacting with the empty space around it in a complex physical way that the old equations simply could not handle. Physics needed a new set of rules to tame the infinities, fix the equations, and explain this tiny shift. Eventually, over years of grueling, exhausting mathematical labor, those new rules were found. And the calculation that came later, once the infinities had finally been dealt with, predicted a separation of 1057.864. Listen to those two numbers again. 1057.862, 1057.864. Hold those two numbers next to each other for a moment. Nature said one thing, and the equations, once they were finally made to behave, said the same thing, out to the sixth digit. That agreement is not a trick. It is not a lucky guess. It is not a coincidence. It is one of the most astonishing, breathtaking triumphs in the history of human thought. The method they used to achieve that calculation, to finally tame the wild, destructive divergences in the math, is a procedure called renormalization. It was developed independently by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, and it was eventually formalized into a workable mathematical structure by Freeman Dyson. Renormalization is a highly complex, fiercely difficult mathematical procedure, but the core physical idea behind it can be explained in very plain speech. The theory of quantum electrodynamics contains certain parameters built into the foundational math, like the mass and the charge of the electron. These are called the bare mass and the bare charge. Think of them as the properties of an electron if it were completely isolated, sitting alone in a truly empty universe. But here is the crucial physical reality. No one, in the entire history of science, has ever seen or measured a bare electron. Imagine a person trying to walk through a dense, crowded room. You cannot measure how fast that person can run on an empty track, because the track is never empty. They are constantly bumping into people, dragging a crowd along with them, slowing down, altering their path. The person on the empty track is the bare electron. The person struggling through the crowd, dragging the weight of the room with them, is the dressed electron. In quantum field theory, the crowd is the electron's own electromagnetic field, and the vacuum of space itself. You can never ask the crowd to leave. You can only ever measure the electron as it exists in the real world, fully dressed in its interactions. Because an electron is always surrounded by its own electromagnetic field, and because that field is always interacting with the vacuum of space, you can never, ever isolate the particle from its environment. What a laboratory actually weighs, what a highly sensitive machine actually measures, is the dressed quantity. It is the electron, together with everything its own field drags along with it. The bare mass sitting inside the pure equations is mathematically infinite. The dressed mass sitting inside the real world of the laboratory is small, light, and perfectly finite. So the physicists did something radically, aggressively pragmatic. They essentially cut the infinite bare mass out of the equations entirely. They took the finite dressed mass that had been measured by physical instruments in the laboratory, and they put it back into the theory by hand. They cancelled the infinities out against each other, hiding them away, leaving only the finite, measurable numbers behind to do the actual predictive work. It worked. It worked so incredibly well that it allowed them to calculate the Lamb shift to that staggering degree of accuracy. It built the foundation for the most precise physical theory ever devised by our species. But it left a deep, cold, lingering unease among the very men who built it. Richard Feynman was not a man easily intimidated by mathematics. He was a brilliant, intuitive thinker who could see through complex equations to the physical reality hiding underneath. He shared the Nobel Prize in Physics for his crucial role in developing this very technique. He helped invent the rules that saved quantum mechanics from the infinities. But when he wrote about renormalization, he wrote with remarkable, almost brutal bluntness. Feynman said that renormalization is a dippy process and hocus pocus. He wrote that it has prevented us from proving that the theory of quantum electrodynamics is mathematically self-consistent, and he openly admitted, "I suspect that renormalization is not mathematically legitimate." Paul Dirac, the quiet, uncompromising man who wrote the fundamental equation the whole edifice stands on, was even harsher. Dirac believed that physics must be built on beautiful, flawless mathematics. He could not accept a theory that relied on a mathematical trick to hide its own flaws. In a lecture given in the year 1975, decades after the Lamb shift had been successfully calculated, Dirac said exactly what he thought of the procedure. "I must say that I am very dissatisfied with the situation, because this so-called good theory does involve neglecting infinities which appear in its equations, neglecting them in an arbitrary way. This is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it turns out to be small, not neglecting it just because it is infinitely great and you do not want it." Dirac never changed his mind. Until the end of his life, he believed that physics had taken a wrong turn, that they had accepted an ugly compromise simply because it happened to give the right answers. He wanted a theory that was logically pure from the ground up, not one that required humans to manually intervene and erase the parts of the math that did not work. That deserves a moment of quiet before we go on. These were not angry critics throwing stones from the outside. These were not rival scientists looking for a flaw to exploit to advance their own careers. They were the architects. They were the men who built the walls and laid the roof of modern physics. And they were the first ones to stand in the middle of the room and say, out loud, that the foundation beneath their feet was deeply suspect. They had built a theory that was more accurate than anything humanity had ever seen. Yet at its mathematical core, it relied on a procedure that its own creators considered to be hocus pocus. It relied on crossing out infinities because they were inconvenient. It is a strange and beautiful contradiction. We can measure it. We have never proved it, and those two sentences do not cancel each other out. The map of reality was fundamentally incomplete, and the math was held together by an uneasy, pragmatic compromise. But the map worked. The equations, however questionable their derivation, perfectly described the physical world. The interactions between the electron and the space around it were not theoretical ghosts. They were undeniable physical facts, waiting in the dark to be measured. The field was already there. What does it actually mean for a space to be empty? Imagine a thick, heavy steel box sitting in the middle of a laboratory floor. If you want to make the inside of that box truly empty, you have to start by systematically removing the physical matter. You attach a heavy industrial pump to the side of the box. You turn the pump on, and it begins to pull. You can hear the heavy, rhythmic thumping of the machinery as it drags every single floating atom of air out of the chamber. You let it run for hours, then days, until the pressure inside drops to exactly zero. Eventually, the air is entirely gone. The chamber is a perfect physical vacuum. There is no air to carry a sound, no gas to breathe. If you were inside, there would be nothing to feel. But you are not finished. The box is still being bombarded by electromagnetic radiation from the outside world. So you wrap the thick steel in layers of heavy lead and fine conductive copper mesh to absolutely block out radio waves, X-rays, and the faint background radiation of the cosmos. You are still not finished. The physical walls of the box are at room temperature, which means their atoms are vibrating, radiating invisible infrared heat into the dark interior. So you plunge the entire massive apparatus into a deep, freezing bath of liquid helium. You cool the steel box down until it is hovering just a tiny fraction of a degree above absolute zero. The freezing temperature drains the kinetic energy out of the metal. All thermal vibration comes to a complete, dead halt. The walls are perfectly still. They emit no heat whatsoever. Now, according to our everyday human common sense, the inside of that heavy steel box is finally perfectly empty. There is no matter. There is no light. There is no heat. There is no sound. There is absolutely nothing left. But quantum field theory completely rewrites the fundamental definition of empty. According to the rules we have spent the night exploring, the space inside that box is permeated by quantum fields. The electron field is there. The electromagnetic field is there. The quark fields are there. And here is the single most important rule about a quantum field. It cannot be switched off. You cannot remove a field from a region of space. The field is the space. You can drain the energy out of the field, reducing it to its absolute lowest possible mathematical value. But, in the strange, probabilistic world of quantum mechanics, a field is strictly forbidden from ever being completely still. Even when it is in its absolute lowest energy state, even when not a single physical particle is present, the field is still fluctuating. It is constantly vibrating, trembling with an irreducible baseline level of energy. You can pump every single atom out of the chamber. You can freeze it to absolute zero. But it is not quiet in the only sense that matters. The dark interior of the box is humming. In the year 1948, a Dutch physicist named Hendrik Casimir made an astonishing prediction based entirely on this invisible hum. He asked a theoretical question. If empty space is really full of restless, fluctuating field energy, what happens if you place two objects extremely close together inside a vacuum? Casimir imagined two perfectly flat, uncharged, parallel conducting plates, placed just a tiny fraction of a hair's breadth apart. Think of the fluctuating fields as waves on an ocean. Because the two plates are so incredibly close together, certain long, rolling wavelengths of the vacuum fluctuations simply cannot physically fit in the microscopic gap between them. They are completely excluded from the inside space. But on the outside of the plates, facing out into the wide-open vacuum of the chamber, there are no restrictions. All wavelengths, short and incredibly long, are allowed to exist. They all crash and push against the outer surfaces of the metal. Because there is significantly more field activity on the outside pushing in than there is on the inside pushing out, the overall vacuum pressure on the outside is greater. It is a tiny imbalance, but it is absolute. Casimir predicted that the two plates should be physically pushed toward each other, as if an invisible hand were pressing them closed from both sides. Think about how incredibly strange this prediction is. There is no electrical charge on the plates. There is no magnetic attraction pulling them together. There is no wind blowing inside the frozen vacuum chamber. There is just proximity and the invisible, restless energy of empty space itself. It took decades for experimental physics to definitively prove Hendrik Casimir right. The force he predicted is unbelievably delicate, easily overwhelmed by the slightest stray static charge or thermal vibration in the environment. But in the year 1997, a physicist named Steve Lamoureux, working at the University of Washington, finally built an apparatus sensitive enough to measure the whisper of the vacuum. Lamoureux's apparatus was a masterpiece of careful, deliberate engineering. He did not use two perfectly flat plates, because aligning two microscopic plates so they are perfectly, flawlessly parallel is nearly impossible in the physical world. Instead, he used a spherical lens, about 1.5 inches across, set against a flat optical quartz plate. Both of these delicate glass pieces were carefully coated with copper and gold to ensure they could conduct electricity perfectly. He took this carefully prepared gold-coated lens and plate, and he hung them from a delicate instrument known as a torsion pendulum. This is not a pendulum that swings back and forth like a grandfather clock. It is a remarkably sensitive mechanical device where the objects are suspended on an incredibly fine, perfectly straight tungsten wire. It is designed to measure twisting. If even the absolute slightest, most microscopic force pushes the lens toward the flat plate, the tungsten wire will twist in response. And that microscopic twist can be measured. It takes unbelievable patience. Lamoureux had to ensure that not a single heavy truck driving on a nearby road and not a single shift in the temperature of the room could interfere with the delicate twist of that incredibly fine tungsten wire. Lamoureux placed this entire delicate assembly inside a heavy, shielded vacuum chamber. The air was pumped out. The world was shut away. And inside that dark, silent space, the gold-coated lens and the plate were pushed together, exactly as Hendrik Casimir had predicted nearly 50 years earlier. The measurement recorded by the twisting tungsten wire agreed with the highly complex theoretical mathematics to about 5%. It was a stunning confirmation. The vacuum was real. Its energy could physically move pieces of metal. And as a matter of fact, it is exactly this same humming vacuum, these same invisible field fluctuations pushing against physical matter that cause the tiny Lamb shift in the hydrogen atom we discussed earlier tonight. Now, we must stop here and put up a very firm, unyielding guardrail. If you have ever read a popular science article, or if you have ever watched a television documentary about the vacuum of space, you have almost certainly heard the phrase, virtual particles. You have probably heard the vacuum described as a boiling, churning ocean of tiny objects flickering in and out of existence. You have been given a mental picture of ghost-like particles popping into reality from nothingness, living for a billionth of a second and then vanishing just as quickly. That is an extremely common, highly seductive way to talk about this subject in documentaries because it gives the human mind an easy, dramatic picture to hold on to. It sounds like magic. It is also deeply, fundamentally misleading. We must be completely honest as we walk through this dark space. We must be clear about what virtual particles actually are, and more importantly, what they are not. They are not physical objects. They are not tiny, hard spheres of matter popping into our reality. They do not exist in the same way that the chair you are sitting in exists, or the earth you are standing on exists. Virtual particles are terms in a calculation. They are entries in a bookkeeping method. When physicists try to calculate the behavior of interacting fields, the absolute true mathematics are often far too difficult and complex to solve exactly. So, they use a highly effective mathematical shortcut called a perturbation series. It is a way of approximating a final answer by adding up smaller and smaller mathematical corrections, one by one, To help human brains follow this incredibly complex arithmetic, physicists draw little diagrams of these mathematical corrections on paper. We draw lines and loops on a chalkboard, and we call those lines virtual particles. It is a brilliant piece of mathematical accounting. But we must never confuse the map with the territory. We must never confuse the accounting tricks on the page with the physical reality of the universe. The Casimir force pushing on Steve Lamoureux's gold-coated plates is absolutely real, and it is physically measured in a laboratory. The Lamb shift is absolutely real. The energy of the vacuum is a physical fact. But the little objects popping in and out of existence are simply a human picture we drew to help ourselves do the difficult math. The continuous field is what is real. The field is the physical entity. The virtual particles are just the ink on the ledger. This realization that empty space is not empty, but instead carries a fundamental, restless baseline of energy, is one of the greatest triumphs of quantum theory. It reveals a universe far more vibrant and alive than anyone had ever suspected. But it leads directly to a cliff edge, because if empty space carries energy, and if the universe is overwhelmingly made of empty space, then the crushing weight of gravity should feel that energy. Every cubic inch of the vacuum should be incredibly heavy. It should warp the fabric of the universe around it, pulling everything inward, collapsing the stars and the galaxies under the absolute mass of empty space. And that is exactly where the whole picture comes apart. We left off standing on the edge of a cliff. Empty space is not actually empty. It carries a fundamental, restless baseline of energy. The quantum fields are constantly humming in the dark, and that hum carries real physical power. But this beautiful realization leads to an immediate, terrifying mathematical consequence. When Albert Einstein formulated his general theory of relativity in the early 20th century, he taught us that gravity does not just pull on physical mass. It does not just act on heavy things like rocks and planets and the dense cores of stars. Gravity pulls on energy itself. Energy and mass are deeply, fundamentally intertwined. They are two sides of the exact same coin. If you take a sealed box and you fill it with blazing hot, energetic light, that box will physically weigh slightly more than a box filled with darkness. Energy gravitates. Energy has weight. So if the vacuum of space itself contains a baseline level of quantum energy, that vacuum energy must gravitate. It must physically weigh something. It must warp and bend the fabric of space, and time exactly the same way a heavy star would. Every single empty inch of the cosmos, from the space between your fingers to the vast, dark gulfs between the distant galaxies, must exert a physical, gravitational pull. If the thought of the entire universe pressing down on you is making your eyes heavy, you have permission to simply drift off. The numbers we are about to discuss are too large for any human mind to truly hold on to anyway. You do not need to fight to stay awake. You can just close your eyes and let the vastness of the history wash over you in the dark. If every single cubic inch of empty space in the universe carries its own weight, and if you add up all the unfathomable oceans of empty space existing between the stars and between the galaxies, then the universe as a whole should be impossibly heavy. It should have collapsed in on itself in a violent, catastrophic crunch, or it should have torn itself apart under its own unimaginable tension long before the Earth was ever formed. The sky above us simply should not exist. But we can walk outside on a quiet night, and we can look out at the sky, and we can see that the universe is not collapsing, it is expanding. And not only is it expanding, but the expansion is actually accelerating. The distant galaxies are flying apart from one another, moving faster and faster as time goes on, driving the universe toward a cold, dark, isolated future. Whatever invisible, relentless force is driving this acceleration is known simply as dark energy. And over the last few decades, astronomers have actually been able to measure it. By painstakingly observing the fading light of distant, exploding stars, supernovae detonating in the deep past, they were able to track how the universe has stretched over billions of years. They found the fingerprint of the vacuum. This dark energy corresponds exactly to the energy of the vacuum itself. The physical measurement tells us that the energy density of empty space is not zero. The vacuum really does weigh something. It is a real number. But it is astonishingly, delicately, beautifully small. It is a tiny, microscopic whisper of energy, gently pushing the universe apart. So, physics finds itself holding two separate, isolated truths. They have a brilliant mathematical theory of quantum fields that says the vacuum must carry energy. And they have a brilliant astronomical observation that confirms the vacuum does carry energy, and it measures exactly how much that is. And then comes the collision. Theoretical physicists sat down to calculate exactly how much energy the quantum fields should be contributing to the vacuum. They began to add up the hum of the electron field, the restless fluctuations of the electromagnetic field, the heavy presence of the quark fields, and all the other fields that make up the known universe. They did the grueling, exhaustive math to see how much all of this invisible vibration should weigh. And the number they got was completely, fundamentally, violently incompatible with the physical reality we observe in the sky. The quantum field theory estimate of the energy density of empty space exceeds the observed value by up to about 120 orders of magnitude. If you have never encountered that phrase before, we need to pause and explain exactly what an order of magnitude is. It is not just multiplying a number by 100 or 1,000. Every single order of magnitude is another zero added to the end of the number. It is another complete factor of 10. 10 is one order of magnitude. 100 is 2. 1,000 is 3. To say that the calculation is wrong by 120 orders of magnitude is to say that the calculation is wrong by a factor of a 1 followed by 120 zeros. To truly understand the scale of this error, to feel the weight of what went wrong, we have to use a physical comparison. Physicists estimate that if you were to count every single star in every single galaxy, every single planet, every single grain of sand, and every single floating speck of dust, there are roughly 10 to the 80th atoms in the entire observable universe. That is a 1 followed by about 80 zeros. It is an unimaginably vast number. It accounts for every single piece of solid matter that has ever been observed by human instruments since the dawn of astronomy. The mathematical gap between the predicted vacuum energy and the measured vacuum energy is significantly larger than that total count of every single atom in the universe. It is larger by another 40 zeros on top. This is a level of wrongness that defies human language. It is a failure so absolute, it is almost difficult to comprehend. It is not that the theoretical prediction missed the centre of the target by a few inches. It is not a rounding error. It is that the prediction and the physical measurement are not even the same kind of number. Because of this unfathomable gap, this specific calculation is widely called the worst theoretical prediction in the history of physics. It gets described in textbooks and in lectures as the largest disagreement between theory and experiment anywhere in science. How does the most successful mathematical theory in human history get an answer so completely, spectacularly wrong. The mathematics of the vacuum contains several different massive contributions. There are massive positive contributions pouring into the equation from the restless zero-point energy of the various quantum fields. But there are also massive negative contributions pulling in the exact opposite direction, arising from something called Higgs condensation. In order for the final calculated number to match the tiny, delicate, whispering value we actually observe pushing the galaxies apart in the night sky, these massive positive numbers and these massive negative numbers would have to perfectly, flawlessly cancel each other out, all the way down to more than 100 decimal places, leaving just a microscopic sliver of energy behind. There is absolutely no known reason they should cancel each other out to anything remotely resembling that level of precision. Nothing in ordinary life cancels like that. A bank that balanced its books to 100 decimal places every night, forever, without ever being told to, would not be described as well run. It would be described as suspicious. There is no known physical law, no hidden mathematical symmetry, that forces the equations to balance that beautifully. And yet, if we are here to talk about it, if the universe has not crushed us or torn us apart, they evidently do. This is the point in the story where a less honest narrator might try to offer you a glimmer of hope. They might tell you about a brilliant new theory waiting in the wings. They might suggest that modern physicists are closing in on the answer, that they have found a clue, and that it is only a matter of time before the equations are finally fixed. We are not going to do that. There is no accepted resolution to this problem. None. No one on Earth knows why the universe is not crushed by the sheer mathematical weight of its own empty space. We are not closing in on an answer. There is no brilliant new equation waiting just around the corner to make the numbers balance. The cosmological constant problem, as it is formally known, is a gaping, open wound in the very centre of modern physics. It is the exact place where our deepest, most flawless understanding of the microscopic quantum world crashes violently, inexplicably, into our deepest, most flawless understanding of the macroscopic universe. The two halves of human knowledge simply refuse to speak to one another. They produce a contradiction so vast it defies belief. And this is the stark, beautiful reality of doing science at the very edge of human capability. It is the willingness to stand in the dark and admit what you do not know. We can measure it. We have never proved it. And those two sentences do not cancel each other out. We can measure the expansion of the universe perfectly. We can measure the intricate interactions of the quantum fields perfectly. But we cannot weave them together. We do not know why the dark vacuum is not overwhelmingly, infinitely heavy. But we know it is there. We know it holds the stars in place, and we know it gently pushes them apart. The field was already there. We have just spent some time looking into the dark, examining a theoretical failure so vast it is difficult to even hold in the human mind. The mathematical theory of the quantum vacuum produces an estimate for the weight of empty space that is wrong by an unfathomable degree. But I want to bring the temperature down now. I want to step away from the edge of the universe, and I want to bring the science much closer to home. Because despite that one glaring massive failure out in the deep cosmos, the theory of quantum fields is overwhelmingly right. And it is right in a way that directly touches your own body, right here in the dark. If you pay any attention to science news, you have probably heard of the Higgs boson and the Higgs field. There is a very common, very pervasive belief, often repeated in popular science writing, that the Higgs field is simply What gives things mass? The story usually goes something like this. The Higgs field is like a thick syrup that fills the entire universe, and as particles move through it, the field drags on them, giving them their weight. That is a beautiful idea. And on a fundamental microscopic level, it is partially true. The Higgs field does interact directly with the elementary particles, like the quarks and the electrons, and it does give them their individual, inherent masses. But if you believe that the Higgs field is what makes you heavy, you are mistaken. The field gives the elementary particles their mass. But it does not give you most of yours. The Higgs mechanism is absolutely essential for the universe to exist in the form we recognize. Without it, electrons would fly apart at the speed of light, and atoms could never form. But while it is responsible for the mass of the fundamental building blocks, it is not responsible for the mass of the finished building. To understand why that is, we have to take the atom apart very carefully. We have to look at the arithmetic. Think about a single proton. The protons are the heavy, stable particles sitting at the very center of the atoms that make up your bones, your skin, the blood rushing through your ears, and the blanket covering your body tonight. Physicists weigh subatomic particles like protons using a specific unit of measurement called mega-electron volts. Do not worry about the specific name of the unit. It sounds complicated, but it is simply a unit of mass energy, nothing more. It is just a scale they use to weigh the unimaginably small. If you put a single proton on that scale, it weighs about 938 of those units. Now, a proton is not a solid indivisible sphere. It is made of 3 smaller elementary particles called quarks, held together in a tight cluster. It is these 3 individual quarks that get their mass directly from interacting with the Higgs field. So, what happens if we isolate the mass of those 3 quarks and we add them together? The masses that the Higgs mechanism supplies to the quarks inside a proton add up to roughly 9 of those units. 9 out of a total of 938. That is about 1%. Think about what that actually means. The physical stuff that makes up the proton, the actual elementary particles themselves, only accounts for about 1% of the proton's total physical weight. Imagine stepping onto a scale and finding out that the physical matter you are made of only accounts for 1% of the number on the dial. So where on earth is the other 99% coming from? It comes from the sheer violence of the environment inside the proton. It comes from the energy of the gluon field and the complex dynamics of what physicists call the strong interaction. The 3 quarks inside a proton do not just sit quietly next to one another. They are bound together by a fundamental force. This force is governed by a property that physicists call color charge. Now, we need to be very clear here, so you are not misled. Color charge has absolutely nothing to do with visible color. Quarks are not red, or green, or blue. They do not reflect light. Color is just a convenient, whimsical name that human beings invented to keep track of a complex mathematical property in the equations. But the strong force generated by this color charge is incredibly bizarre, and it behaves unlike any other force we encounter in our daily lives. Think about electromagnetism. If you have 2 strong magnets and you pull them apart, the invisible magnetic force between them gets weaker and weaker the further away you move them. Eventually, the force fades away entirely, and the magnets are free. The strong force does not do that. The strong force does not fade away as you pull quarks apart. The tension in the gluon field connecting them just grows stronger and tighter and more fiercely resistant. It is like pulling on an incredibly heavy, infinitely strong steel spring. And if you put enough energy into the system, if you pull hard enough, the spring does not simply stretch forever. It snaps. But because you have pumped so much raw physical energy into the field by pulling on it, that stored energy instantly converts into mass. Instead of pulling one lone quark free, the snapping field creates entirely new particles out of the vacuum to cap off the broken ends. It is exactly like trying to cut a bar magnet in half to isolate the North Pole. You do not get a lone North Pole, you just get two smaller magnets. Because of this, you can never isolate a single quark. They are permanently locked together in a phenomenon called confinement. And holding that intense, violent knot of energy together costs a staggering amount of power. The gluon field inside the proton is a raging, churning storm of strong interaction energy, constantly binding and rebinding the quarks. And as Albert Einstein taught us over a century ago, energy has weight. Sit with that for a moment, because it is not an abstraction, it is a fact about the body you are lying in right now. Feel the weight of your own hand resting on the blanket. Feel the heaviness of your own body pressing down into the mattress. Notice the way gravity pulls you steadily toward the center of the earth. That weight is overwhelmingly not stuff. It is not solid material dragging you down. Your hand is heavy because it is made of atoms. The atoms are heavy because they are made of protons and neutrons. And the protons and neutrons are heavy because they are filled with the churning, fiercely bound energy of the strong interaction. You are not heavy because you are full of solid material. You are heavy because binding costs energy, and energy has weight. 99% of the weight of your own body is just the energy of a quantum field, held permanently in a tight, unbreakable knot. This is the profound beauty of the standard model of particle physics. When it is right in a way that rewrites our entire understanding of what it means to physically exist. But it is not a religion, it is a science. And science requires a fierce, uncompromising honesty, especially when the mathematical theory seems to disagree with the physical laboratory. There is a subatomic particle called the muon. It is essentially a heavier, unstable cousin of the familiar electron. For many years, physicists carefully measured the magnetic properties of the muon, and they compared those physical measurements to the massive, complex mathematical predictions generated by the theory. For years, the muon's measured magnetism sat apart from the predicted value. It was a tiny discrepancy, but in the world of high-precision physics, a tiny discrepancy is a blaring, inescapable alarm. It looked for all the world like the first real, undeniable crack in the foundation of the standard model. It looked like the mathematics were finally failing to describe reality. Then came the data from Fermilab, a massive particle physics laboratory built on the wide prairie outside Chicago. Fermilab is not a laboratory on a tabletop. It is a vast ring of superconducting magnets, wide enough to hold a stadium, designed to send particles racing around it just to catch a fleeting glimpse of how they behave. It took an army of physicists and engineers years to design, build, and run the experiment. They had to account for every stray magnetic field, every slight variation in temperature, and every tiny imperfection in the steel. In June of 2025, they released their third and final measurement of the muon. It was an experimental triumph, the result of years of incredibly delicate work. They achieved a precision of 127 parts per billion. This was even better, even more exact, than the 140 parts per billion the machine was originally designed to reach. Almost simultaneously, the theoretical physicists working in the Theory Initiative released an updated, highly refined mathematical prediction in May of 2025. They had pushed their massive supercomputers to the absolute limit to refine the calculations. The theoretical prediction is not a single equation you can write on a napkin. It requires something called lattice quantum chromodynamics, a mathematical method of simulating the chaotic, boiling interior of the vacuum by breaking space and time themselves into a grid of points, 4 dimensions of it, and solving the whole thing point by point. It takes months of continuous calculation on some of the most powerful computers on Earth just to coax a single number out of the darkness. And when they laid the new measurement next to the new prediction, the gap was gone. The theory and the physical measurement now agreed with one another, sitting comfortably within the margins of experimental uncertainty. Now be careful with this, because it would be easy to tell it wrong in either direction. We do not say that the anomaly was definitively disproved, and we absolutely do not say that the possibility of new unknown physics has been permanently ruled out. What we say is that the gap narrowed from the theory side. What looked for years like a crack in the physical wall, what looked like a genuine failure of the equations, may have simply been a limit in our own human arithmetic. The theory was right, we just had not calculated it precisely enough yet. It is a humbling reminder that when the universe seems to disagree with us, sometimes the universe is quietly trying to tell us that we need to look harder at our own work. The gap did not close because the physical universe changed its mind. It closed because the humans doing the math got better at doing the math. And the theory side of the muon problem is still not fully settled. Even tonight, there is an ongoing, deep tension between 2 entirely different ways of doing the calculation. The argument is still happening. The numbers are still being checked. But the theory is this good. It is this incredibly careful. It is this fiercely self-correcting. The physicists argue over parts per billion, and they do not stop until the mathematics and the physical world align perfectly, which is exactly what makes the very last thing we have to discuss tonight so profoundly strange. The field was already there. In the year 2000, the Clay Mathematics Institute in Cambridge, Massachusetts, made an announcement that captured the attention of the world. They published a formal list of the 7 Millennium Prize problems. These were carefully determined to be the 7 most difficult, the 7 most profound, and the 7 most important unsolved mathematical problems in the entire history of human thought. To ensure the world took them seriously, the Institute attached a staggering bounty to the list. Anyone who could definitively solve just one of these 7 problems would be awarded a prize of $1 million. More than 2 decades later, as you lie here listening to this, 6 of those 7 problems remain completely unsolved. One of those remaining undefeated problems is called the Yang-Mills existence and mass gap problem. The formal statement of the mathematical challenge asks for a rigorous proof that a non-trivial quantum Yang-Mills theory exists in 4 dimensions and that it possesses a mass gap strictly greater than 0. We need to translate that formal, dense mathematical language into plain speech because the physical meaning of this problem is absolutely unmistakable, and it is deeply personal. Yang-Mills theory is the foundational mathematical framework behind the strong nuclear force. It is the exact mathematics that describe how the gluon field binds quarks together. It explains the mass gap, the reason why the strong force only operates over incredibly tiny distances, locking matter tightly into dense cores rather than stretching out forever like gravity. In short, it is the equation for the heavy churning storm of energy that holds together every single atomic nucleus in your body right now. It is the reason you have physical weight. It is the math that allows solid matter to exist in the universe. We know, as a matter of absolute, undeniable physical fact, that the strong force works. You are made of it. Your bones and your blood rely on it. But mathematically, no human being on Earth has been able to construct the theory rigorously in the 4 dimensions of space and time that we actually live in. Brilliant theoretical physicists and mathematicians have managed to find rigorous mathematical constructions on paper, but only for hypothetical, flat, simplified worlds of lower dimensions. In an imaginary universe of 1 dimension or 2 dimensions, the math can be made to work perfectly. But in our sprawling, incredibly complex 4-dimensional universe, the rigorous, flawless mathematical proof simply does not exist. No one has claimed the $1 million. The mathematicians who have tried have found themselves lost in equations that refuse to resolve. They have found that the mathematics of the strong force are so intensely non-linear, so deeply tangled, that our current human mathematics simply lack the vocabulary to describe them rigorously. The fundamental engine of your own body, the force that gives you mass and keeps your atoms from flying apart, remains a deep mathematical mystery. And the cracks in the theoretical foundation go far deeper than just the strong nuclear force. There is an obscure but devastating mathematical result known as Haag's theorem. To understand why it matters, you have to understand how physicists actually do their daily work. Almost every successful, practical calculation in quantum field theory uses a mathematical scaffolding called the interaction picture. It is the absolute bedrock of perturbation theory. It is the method of adding up those tiny virtual corrections that we talked about earlier tonight. The interaction picture relies on a very specific, fundamental assumption. It assumes that you can mathematically relate a completely free, empty, quiet vacuum to a vacuum that is actively interacting, boiling, and churning with fields. It assumes you can start with a still lake and mathematically turn it into a raging ocean without breaking the equations. Haag's theorem proves, with absolute, flawless mathematical rigor, that you cannot do this. It states that for a genuinely interacting relativistic quantum field theory, the interaction picture simply does not exist. You cannot draw a smooth mathematical line between a vacuum with no particles and a vacuum filled with interacting fields. The mathematics break down completely. The two states are fundamentally, strictly incompatible. The underlying assumption is completely false. The mathematical scaffolding that the entire field relies upon is, technically speaking, illegal. And yet, we find ourselves staring at a magnificent, almost comical contradiction. This illegal scaffolding remains the only genuinely practical method any physicist has ever found for making realistic calculations. It is mathematically forbidden, and it works spectacularly well. It has produced the most phenomenally accurate numbers ever written down by human hands. Then, there is the problem of the parameters. A beautiful, pure, elegant mathematical theory should theoretically be able to explain the universe from first principles. You should be able to write down the fundamental equation, and everything else in the universe should naturally flow from it, without requiring human intervention. But the standard model of particle physics is not pure. In its minimal form, before the tiny masses of neutrinos were eventually folded into it, the standard model contains exactly 19 fundamental numbers that it simply cannot derive. Think of these 19 numbers like control dials on a massive, complex machine. The dials include the masses of the various elementary particles, the coupling strengths of the different forces, and the intricate mixing angles that determine how particles transform into one another. The machine works flawlessly. But the theory does not predict where the dials should be set. It has absolutely no idea why the top quark is incredibly heavy while the electron is incredibly light. It cannot tell you why the dials are set to those exact numbers. Roughly 13 of them come directly from the incredibly complicated, messy way that the particles couple to the Higgs field. The most successful theory in history cannot calculate how heavy an electron is. It has to wait, with its hands open, for an experimental physicist to go into a laboratory, build an enormous machine, physically measure the weight of the electron, and hand that number back to the theorists. Only then can they manually plug the number into the equations and carry it forward to make their predictions. The theory does not explain the 19 parameters. It merely accommodates them. And look at what the framework completely leaves out. Look at what it cannot explain at all. It leaves out gravity entirely. Albert Einstein published his general theory of relativity in the year 1915. More than a century later, it remains our absolute best, most heavily tested description of how gravity actually works in the macroscopic world. But there is still no complete, experimentally confirmed quantum theory of gravity. The equations of the quantum fields and the equations of the curving cosmos simply refuse to talk to one another. They speak entirely different mathematical languages. General relativity describes a smooth, continuous, gently curving fabric of space and time. Quantum mechanics describes a chaotic, jumping, probabilistic world broken into tiny, discrete packets. When physicists try to force the two theories together into a single equation, the mathematics explode into infinities that cannot be renormalized away. They simply refuse to merge. The model offers absolutely no account of dark matter. When astronomers look at spinning galaxies, they can see that there is not enough visible matter to hold them together. There must be an invisible gravitational scaffolding holding the stars in place, but the standard model contains no particle that fits the description. It offers absolutely no account of dark energy. It cannot explain the relentless whispering force that is currently pushing the cosmos apart, driving the galaxies into isolation. Even the simple, undeniable physical fact that neutrinos have a tiny amount of mass required physicists to go back and manually extend the original model after the fact, because the original mathematics assumed they weighed absolutely nothing. The map is unfinished. The edges of the parchment fade into total darkness. So now, we must close the loop. I want you to leave the vastness of the cosmos behind, and I want you to return to the opening image we started with tonight. Return to the quiet, dark basement laboratory. Listen to the steady, rhythmic hum of the heavy industrial pumps. Picture the heavy steel vacuum chamber, the powerful magnetic fields, the cold held steady just above absolute zero. Picture the single electron held entirely alone in its trap, suspended in the dark, cooled to a tiny fraction of a degree above absolute zero. Think about the men and women who spent years of their lives carefully, painstakingly measuring the magnetism of that single electron, fighting through the noise, pushing the absolute limits of human engineering just to extract a number from the dark. Think about the number they pulled out of the machine, accurate all the way down to 14 decimal places, 1.00115965218059. And then think about the theoretical physicists working on whiteboards and supercomputers, using the theoretically illegal scaffolding of perturbation theory, manually plugging in the measured parameters that the theory cannot explain, crossing out the infinities by hand to calculate that exact same number. Both of these things are true at the exact same time. The most exact agreement between a mathematical prediction and a physical measurement in the entire recorded history of our species sits directly inside a mathematical structure that nobody has yet proved is even mathematically coherent. I want you to lie there and let the immense quiet weight of those two facts press fiercely against each other in the dark, because this is the entire point. This is the lens we have been carefully building all night. This deep, lingering tension is not a scandal. It is not a failure of the scientific method, and it is absolutely not a cynical debunking of modern physics. It is exactly the opposite. A scientific theory that is willing to say out loud exactly where it stops working is infinitely more trustworthy than one that does not. A theory that admits it cannot explain the weight of an electron, a theory that openly publishes its own profound contradictions and offers $1 million to anyone who can fix them, is a theory built on fierce, uncompromising honesty. If someone hands you a map of the world, and that map claims to have every single path, every single ocean, every single mountain, and every single shortcut perfectly and flawlessly charted, they are usually trying to sell you something. But if they hand you a map where the known roads are drawn with microscopic precision, while the edges of the paper are left deliberately blank, you know you are holding something real. The map we have is astonishing. The map is unfinished. And both of those facts are profound reasons to trust it. We have reached the end of the road. We have measured the deepest foundations of the physical universe, and we have found that they are held together by a beautiful necessary tension. We can measure it. We have never proved it. And those two sentences do not cancel each other out. The universe is not a solid, static thing. It is a vibrating, restless expanse. You are made of fields, and most of your weight is the energy it takes to hold them knotted. Long before we were here to build the machines, long before we were here to write the equations and argue over the infinities, the truth was already humming in the vacuum. The field was already there. If you are still awake, or if you are drifting somewhere quiet on the very edge of sleep, there is no need to hold tightly to the mathematics we have wandered through tonight. You do not need to remember the complicated names of the scientific conferences, and you certainly do not need to hold the exact decimal places of the microscopic measurements in your mind until morning. If you let all of the heavy arithmetic go, if you let the history and the arguments of the 20th century gently fade away, you are left with just the immediate physical reality of the room around you. You are left with the dark air resting against your skin and the quiet, slow settling of the house around you in the night. We all grow up believing that the world is fundamentally made of hard, solid things. We are taught by our everyday human experience that we are solid objects, and that we rest heavily upon other solid objects. We trust the floor to hold us. We trust the bed to support us. But one of the most profound, beautiful realizations of the last 100 years of physics is that solidity is not a basic, passive ingredient of the universe. It is an astonishing, fiercely active achievement. And that does not mean the solidity is a trick, or that the bed is somehow pretending. The bed holds you. That is real. It is simply that the holding is being done by rules and by fields, rather than by tiny bricks stacked tightly against one another. As you lie there in the dark, the mattress beneath you is not just a heavy block of dead, silent material. It is a dense, incredibly complicated, vibrating knot of quantum fields. The resistance you feel, the steady, comforting pressure pushing back up against the weight of your resting body, keeping you from falling through the floor, is not just dead matter bumping into dead matter. It is the intricate, churning machinery of the strong interaction and the Pauli exclusion principle, working endlessly in the dark to keep the fields from collapsing in on themselves. You are resting in a web of invisible forces that stretches out from the center of your own beating heart, moving out past the physical walls of the room, across the silent, frozen gulfs of the solar system, and all the way to the very edge of the observable cosmos. Every single breath you take, and every slow, steady beat of your resting heart is governed by the exact same subtle humming vacuum that dictates the movement of the distant, ancient galaxies. And you do not have to fully understand the mathematics for the mathematics to hold you safely. Long before we had the heavy, complex machinery required to measure the tiny magnetic spin of a single trapped electron, long before we had chalkboards and equations to calculate the infinite weight of the vacuum, long before there were any human beings at all to look up and wonder what the dark was made of, the structure was already there, holding everything together in the cold. The field was already there. And the simple fact that there is still a deep, unresolved mystery at the absolute bottom of the equations is not something that should make you feel fragile, or isolated, or frightened. The fact that the map of reality is fundamentally unfinished does not mean that the ground beneath you is going to suddenly give way. It simply means that the universe is far deeper, far older, and far more complex than the arithmetic we have managed to invent so far. It means that there is still room left for absolute wonder. The territory is still wild, and the mystery is still alive, and we are allowed to simply exist inside of it without demanding that all the numbers balance perfectly tonight. When we meet again next time, we are going to return to that vast, quiet expanse of empty space. We are going to look at the cosmological constant again, but we are going to approach it from the other side of the mirror. We are not going to talk about the sheer, staggering size of the mathematical error between the prediction and the measurement. Instead, we are going to sit quietly in the dark with the profound question living underneath it. If the quantum fields are constantly humming with restless energy, and if the vacuum of space is truly boiling with unavoidable microscopic activity, then why does empty space weigh so nearly nothing, when everything our theories tell us says it should weigh almost infinitely much? Why is the entire universe light enough to simply survive, instead of instantly crushing itself out of existence under its own weight? We will not promise you a neat, flawless mathematical answer, because modern physics does not have one to offer yet. But we will map the exact shape of the question, and we will look at the long shadow it casts across the cosmos. For now, though, you can let all the profound, heavy questions go. You can let the quantum fields do the heavy, silent work of holding the world together while you rest. Wherever you are listening, and whatever time it is, sleep well. This is the unknown.